Great, yeah. So first, I'll say that the idea behind the sonification or the need for sonification arose from the iData project, where we were we're developing this online tool, this web application for viewing and processing and analyzing astronomical images. Part of iData was, through the user-centered design process, try to make sure that that application is accessible. So one feature, one component of the overall application was sonification. There were a lot of other parts to it, but of course that's what I'll focus on today. So when we discussed the need for sonification and kind of talked about what we wanted to achieve with it, there were a lot of things we wanted to achieve, but I would like to just spend just a minute here talking about what our goals were. My main two projects that I work on are the Skynet Robotic Telescope Network and then this, Afterglow Access. So coming from Skynet, coming from the Robotic Telescope Network, we have a website where students and researchers go to submit their observation requests, and then those observation requests go into a queue, and then we're responsible for automatically dispatching those telescopes and then acquiring the data and then getting that data back to the user. So for years now, have seen students in labs and other places visit our site for the first time, and when we ask them to choose a target of their own to observe, they typically will use a sky viewer tool, kind of like planetarium software that we wrote, that allows them to simply click on targets of interest that are visible at the site they want to observe at, and then they will view the DSS preview, so the catalog digital sky survey preview image that we provide. That's what they use to choose what they want to observe. They just keep clicking on different objects, visually inspecting what that preview image looks like, to kind of build some sort of connection with one of the objects, and that's what they end up submitting their request for, because they like the way it looks. So I like the idea of this sonification tool providing a more accessible way of doing the same thing. So imagine, instead of clicking on targets, you can provide the kind of the tabular form of a list where the user can filter by object type, by object visibility, and then as they move through the list, instead of seeing the digital sky survey preview, we can generate a sonification of each of those thumbnails. And based on the sonification, they can make a connection, regardless of what that sonification is or even how it maps to the image. That's kind of irrelevant in this example. It's more about just forming that connection and allowing the user to distinguish between the items that are in the list. So we have not integrated that yet, but that will be a part of the next version of the website that we're going to release for the Skynet Robotic Telescope Network. But moving on to Afterglow Access, this is, of course, where the students and researchers can go to analyze the data, not just from our network, but from anywhere. And so the goals for the sonification algorithm within Afterglow Access was more for identifying and locating targets of interest, as well as detecting some of the common problems that you might encounter with observational astronomy. A lot of the data that people use are coming straight from our telescopes, and so you may have problems with pointing. These are not catalog images. You may have tracking issues, focus problems, saturation. So that's kind of another thing we really wanted users to be able to extract from that sonification. So I'll do a quick demo here with some sample images. In the future, later on, if you want to go back through some of these, I made a more accessible version of this. Afterglow Access is very accessible. We did focus on that, but setting up user accounts and all of the other issues, it became too much to try to tackle before this meeting. So I did create a separate page where the link is in I think Kate has it, and she could put it in the chat if she wanted, but this is a very simple HTML file, so screen readers shouldn't have a problem with it. It's a list, and each list item is a JPEG followed by the sonification of that JPEG. So you can always follow along or play those independently. Within Afterglow Access, though, is what I'll be using, so that's what I have up on the screen right now. So with all sonification algorithms, there's kind of a training period where you need to try to teach the user how to map what they hear into what is on the screen. And so what the iData educators came up with is kind of some sample, just use shapes or use some sample images that are not real astronomical images, but synthetic images that can serve as a good demo. So I'm going to try to share the audio here. FIA has me a little nervous about the time lag because I haven't tested this before, but I'm going to switch to the sonification view. And currently on the screen, I have an astronomical image that is fake. It's a synthetic image in which I've placed a single star in the center. The way this algorithm works is we scan the image vertically. So we start at the bottom and we work our way towards the top. And for each row in the image, we essentially are looking for sources, anything that's bright. And depending on where the source is, we play a tone. And for sources that are to the left of the image, those are lower frequency tones, and sources to the right are higher frequency. So time domain, as time goes on, you're going to be sweeping upward. So things that you hear at the end of the recording or at the top of the image, things that you hear at the beginning or at the bottom. Things you hear that are lower frequency or to the left, higher frequency or to the right. And lastly, because there are images where you might not have anything, it might have been a cloudy night, we do provide indexing sounds. So you're going to hear a ding at the beginning and a ding at the end. And that tells you when the recording started and when it stopped. So I'm going to hit play and we'll just see how this goes. So the ding, it started. You heard some kind of background noisiness, some fuzziness, some slight tones, but then about halfway through the recording, where the center of the image is, you should have heard a full tone representing that single star. So let's move on to another image, which is the next one I've called vertical, which is 3 stars. They are in a vertical line running through the center of the image. So I'm going to hit sonify. Okay, so 3 tones, all the same frequency, separated by about the same amount of time, since they're spaced evenly. Next one is a diagonal, so now we have 3 stars again, but they're moving from the lower left corner up to the upper right, with the center star being in the center of the image. Okay, and then last, there's a horizontal, where the 3 stars are in a line horizontally running through the center of the image. So tones all at the same time, but different frequencies kind of adding up together. So the last part of the training that we had talked about in iData is to have shapes. So it's, you know, for kids in particular, saying, hey, this is where you could start to get into the process of just playing the sound and say, what shape might this be? There's still 3 sources here, 3 stars. What shape might they be in? And so that's an isosceles triangle. So you've got the base at the bottom that's parallel to the bottom of the image. So there were 2 tones that occurred at the same time, followed by towards the end of the image, you had that tone at the top that's in the center. And the last shape, and then we'll do some real images, is a square. And so I think everyone at this point probably knows what that's going to sound like. All right, so moving on to real images. So this next one's just kind of a typical star field, so there's nothing really special about this. I will say that there are 2 different components to the sonification. So we knew that we wanted to get point sources through tones, but I think Gary brought this up just a minute ago, noise. Noise is a big part. And so if you kind of do a separate mapping of the noise in the image, and we basically convert that into white noise, and we play the white noise louder on one track, one stereo track versus the other, depending on whether it's on the left side or the right. We do the same for the tones, by the way. It helps reinforce, we think, the lower frequencies are played louder in the left, higher frequencies louder in the right. So there is a noise component to this as well that is representative of the background noise that is in the image data. So here's a standard star field. So pick up on the, pretty much the individual stars that are in there. Some are brighter, obviously louder, they come out more. Go to a globular cluster, which is, as you can now imagine, would be really fun to listen to. So you heard some of that noise there that's being picked up towards the center of the image too. There's a little bit of a fuzziness there. But yeah, imagine being on a website and trying to choose which target you want to observe, and you hear that, and you're like, yep, that's the one. That's what I want to take a picture of. So you don't even need to see what that looks like, just it sounds really cool. Here is a galaxy. This is where that noise will play a role. So that white noise comes through as the extended source of the galaxy, but right as you're crossing over the core of the galaxy, you kind of get a tone because the core it kind of stands out above the background as a source. Now this kind of goes back towards. I just want to spend just a minute on identifying targets of interest. You can see how it is easy to confirm using the algorithm whether you did have the globular cluster in your center of your field of view, or maybe the pointing was off on the telescope and you were too far. Maybe it's in the upper right corner. You can determine that, but think about tracking was off, or maybe you even had a satellite that was passing through your field of view and might have ruined your data. Here is an image of a galaxy with a satellite passing through. So yeah, that's pretty cool. Like hit your finger on the piano and pull it across there, since the asteroid's moving from left to right, almost horizontally. So we've done some work on planets. It works on planets. The nice thing is this is working on raw image data, so it doesn't matter what image you throw at it. We're not actually assuming that there must be stars and we find the stars. We are taking the raw pixel data and converting it into what you're hearing. So we can throw all sorts of things at it. This is Saturn. Pretty boring for most of the image. So with Afterglow Access, you are able to interact with the algorithm some. You can change some of the parameters like duration and tone. And so you can zoom in, and in Afterglow Access, zooming in, you can reframe what the sonification is. So if we zoom way in on Saturn, now we're basically subframing the image. So now we're zoomed way in on Saturn. And so, of course, zooming in with your mouse, as I was just doing, is not very accessible, but we did build a component in the sonification that allows you to navigate based on what you heard. So I heard something towards the end of the sonification, so you can click a button that's based on time navigation. You heard it was kind of central frequencies, so you can navigate by frequency, play it again, and then you'd find that also it was kind of midway through the sonification and was also still central frequency. play it again. So it's a way to kind of zoom in on a region of interest based on what you were hearing instead of using your mouse. Last thing is an asteroid. Asteroid's kind of similar to a satellite. In particular, if you stack images together, the asteroid's in a different place, and so you combine them all, and you'll end up with a streak similar to the satellite. But I'll just play this one and end there. Okay, so that's the sonification algorithm, and I don't know, I'm probably out of time, but I could maybe take one question. And definitely looking forward to any feedback. Please feel free to even after the meeting, let us know what you think and ways to improve. And we certainly look forward to future opportunities to test this.